look at infinite arithmetic series. We're going to take a look at infinite geometric series. Now, we've already learned about geometric sequences in series, so this should be easy to grasp. So let's first classify it as whether being convergent or divergent. This largely depends on the common ratio r. So if the absolute value of r is less than 1, which means r is between, in other words, r is between -1 and 1 without including these two values, it's going to approach a finite sum, just like the ball that was bouncing. It's going to approach a finite sum of its distance, but it might never reach it, because it keeps going on and on and on, and it's at infinity, and we can't find that. That's impossible. It's unreal. But if the absolute value of r is larger than or equal to 1, it is divergent. Because, well, let's just take an easy example. 1, 2, 4, 8, and it keeps going. And we don't see something that can necessarily find the sum here, because it just approaches positive infinity as it goes on. And we see that if r was negative, it still wouldn't work out. For example, 1 minus 2 plus 4 minus 8. We don't see something obvious that we can work out here. So depending on the number of the term, it's either going to be approaching positive infinity or negative infinity. Again, depending on the placement of the term that we're ending on. But since infinity doesn't even exist, like, it's not a real thing, we can't just end on the infinite term. That's not how it works. So this is also divergent, because it does not approach a finite sum that we can find. And here we have the formula for finding the sum of an infinite geometric series. Note that this formula only works if the absolute value of r is less than 1. That is very important. Please remember this. This formula does not work for anything other than this, under this condition. Because, again, as stated in the previous slide, you can't just find the sum of an infinite terms if it just approaches infinity. So let's analyze this formula and prove it. It says on the top that the first term divided by, on the bottom, 1 minus the common ratio. So how do we prove this? Well, here is the proving process. You can see that the same formula is here dropped onto the bottom. And now let's prove it. So previously we learned that geometric series can be written like this. In last lesson we learned that it can be written like this. Now if we multiply both sides by r, we get this. And now if we subtract the new one from the original, we just get a. Now it might look like the a3 cancels out with this one and the a4 has nothing to cancel out with, but that's not the case because it's infinite. So the a infinite, which doesn't really exist, will cancel out with a infinite eventually. They will both cancel out. So we're only left with the first term. Now, what we have to do is factor out s right here. And now we divide both sides by 1 minus r, so we get the formula right here. Now, if this seems a little bit sketchy to say the least, there's another way of proving it. But it involves limits, and I kind of want to display it here because it's just very important to know how formulas are proven in order to understand questions. So here's the second way of proving the formula. And just as a note before we begin, you don't have to know this. This is limits and stuff. This isn't required to know. In fact, all of the proving isn't really required, but I still love to show them because it is important to understand why the formulas work and not just apply them and memorize them. So we originally had the formula a divided by 1 minus r. And now if we use limits as n approaches infinity, on this equation, we just take a small part of it. R to the nth power will approach 0. Notice that the this, the prerequisite, for this to work, it still applies from the previous proof. So the absolute value of r still has to be less than 1. And now, if it's less than 1, as we keep going up and higher powers, r is going to get smaller, smaller, and smaller. And at one point, when it's finally approaching infinity, r to the nth power is going to approach 0 right here. So now, we already proved this formula in a previous video. And now if we approach infinity with n approaching infinity, this will approach 0. So now at s infinity, it's going to be 0. So a times 1, which is a divided by 1 minus r. This involves limits, so it's not required for you to know this. But it is really helpful to just know how the formulas work.